Hello everyone, I'm Paul and I'll be presenting our work Unveiling Graph Copycats, Inference Attacks with Student Models. Graph neural networks take topology data and Euclidean data, combine them into graphs for the graph neural network algorithm, which works using message passing. This means that a node takes information from other nodes in its neighborhood, aggregates them to update its own representation, which is sent to a feed-forward neural network for downstream tasks like prediction on nodes, edges, even on the whole graph. In 2021, Zhang et al. Noticed that graph neural networks incur additional bottlenecks with regards to fetching neighborhood information during inference. Instead, they proposed training a student NLP model from a teacher GNN using knowledge distortion that was proposed by Hinton et al. In 2015. This combines cross-entropy term with a KL divergence between the student and the teacher's soft targets to create a graphless neural network. The graphless neural network now does not have neighborhood fetching, has faster time to prediction, and now has all the necessary relational cues. In 2020, Duro et al. Showed that members and non-members, in this case members are nodes that belong to the training set of a teacher, non-members are nodes that do not belong to the training set of the teacher. They quantify this and saw that the members and non-members belong to different distributions. In 2021, Olatunji et al. Were able to discriminate between members and non-members. In our case, we say that distilling from GNN to graphless neural network is a form of data minimization, since the graphless neural network now does not have access to relational data during inference. The question we ask is that, does this lead to more privacy? What we did here was did an experiment with 100 trials to look at the similarity between the student and the teacher before and after distillation. And what we noticed is a rightward shift in the similarity after distillation, which shows that distillation leaves behind a signature, which an attacker may be able to leverage to discriminate between members and non-members. And so, maybe distillation does not lead to more privacy. We also check the confidence before and after distillation, and what we see is that confidence values over around the y equals to x line, and what that tells us is that confidence does not change much post distillation, and maybe distillation does not have much effect on privacy. With this at the back of our mind, we designed a reconstruction error attack. The assumption here is that the attacker has only query access to the student model. The attacker has an attack model, a shadow data set from the same distribution as the private training set, and that the student and the teacher are trained from using the same data set. The attacker passes the target graph through the attack model and the student model, combine the posterior, and feed this into a feature extractor that has been trained with a mean squared error. Using the error, the attacker chooses a threshold, and if the error during testing is greater than this threshold, the attacker says the node is a member. Otherwise, the node is not a member. In evaluating this attack, we see that with a very high AUC score, in some cases up to 0.9, the attacker can discriminate between members and non-members. We tried 5 combination methods and we noticed that the ratio method gives us the best results. In the previous setting, We assume that the same data was used to train the teacher and the student, but in realistic scenarios, this may not be the case. Different data sets may be used to train the teacher and the student. In addition, we used an average case metric AUC. The attacker instead should be interested in being able to recognize the most vulnerable cases, even if they are small. And so the attacker is interested in a higher TPR at a fixed FPR. Let us look at two attacks, attack X and attack Y. And attack X has an AUC of 0.88, while attack Y has an AUC of 0.72. Now, even we could say attack X is better than attack Y, but TPR is not directly correlated with AUC, and so let's say at a fixed FPR of 0.1, attack X has a TPR of 0.001, which is lower TPR than FPR. But attack Y has a TPR of 0.40 at that FPR. Now we can say that when budget is tight, X is a poor membership predictor since FPR is higher than TPR. In fact, we can argue that it is a good non-membership predictor, and Y is a much more reliable predictor of membership. And so instead of using the reconstruction error attack, we use the quantile regression to discriminate between members and non-members, using the hinge score, which subtracts the maximum logit for other classes from the true class logit. We subtract the score of the attack model from the student model and feed the results and use the results to discriminate membership. But when this score is less than what is predicted by the quantile regression model, the attacker says the node is non-member, otherwise it is a member. The problem with quantile regression, however, is that it does not have correction for finite samples, so we use the conformalized quantile regression model, which does not assume any distribution of the underlying quantile regression model and does not have asymptotic assumptions. Using non-conformity score, we were able to adjust the quantile of the empirical distribution for finite calibration set size of the conformalized quantile regression model, and then define a prediction interval which helps us to have a better threshold for prediction. Testing using the conformalized quantile regression, we see that in many cases, using different temperature values, the attacker can reliably discriminate between members and non-members for the most vulnerable cases. We wanted to check if the structure of the network has effects on vulnerability. Using node degree as proxy, we notice that node degree is not correlated with vulnerability at all, and but that confidence and entropy shape vulnerability. In fact, when confidence is high, entropy is low, and when entropy is high, confidence is low. In addition to node membership inference attacks which we've been doing, we also checked if we could reliably perform property inference attack, and so we divided node degrees into low degrees, medium degrees, and high degree. The motivation here is that an attacker may want to know which node is influential, and using different machine learning algorithms including logistic regression, random forest, or even an MLP, we see that in some cases with an accuracy of 90%, the attacker can know if a node is influential or not. We also tried link stealing attack, where an attack takes the posteriors of two nodes, compare them by computing distance metrics over them and looking at how similar they are to know if they are connected in the original training set or not. And despite the fact that the attacker has access only to the posteriors from the student's model, with a very high AUC, in many cases greater than 0.8, the attacker can know whether two nodes are connected in the original GNN or not. In conclusion, we now know that knowledge distillation in GNNs does not eliminate privacy leakage, and that student models can reveal information about the teacher's training data. fact, our proposed attack is robust across datasets and low false positive rates. Thank you.